Alright, so the plan today, gentlemen, is that what we want to do is to look at metallic bonding, okay? Obviously we're recording the lesson for posterity purposes, alright? Or for anyone that's not here, like poor old Joed, alright, who can then come back and look at it later. So I said before this lesson, when we had our lesson on Friday, that we've done all the stuff on atomic structure and all the foundational stuff for chemistry. And so over the next few weeks, what we're going to do is look at what I consider the meaty stuff for chemistry. So when we talk about how things combine, okay, how bonds are formed, this is like number one importance for chemistry, because it will come back in stage 2. Everything in the classroom is based on some sort of a structure, some sort of a bond between an atom and an atom forms pretty much every piece of matter that we've got in the room, and I'm breathing it in as well, alright? So the focus for today really is just metallic bonding. And when we did this on Friday, what we talked about for metallic bonding really was only what atoms are involved in metal structures. That's what we talked about on Friday. So we simply said when one metal bonds with another metal, we said that that forms a metal, funny enough. But I did ask you on Friday, was the structure continuous? And what was the conclusion about whether a metal is continuous or not? Anyone remember on Friday? I used the example, okay, when we talked about water and we just introduced you to some ideas, and I used the idea of like water. So here's our water structure. Jack? Oh, well, whenever we have a lesson? Thursday. Lewis? Continuous covalent. All I asked was, is the structure, is it continuous or are there individual parts to a metal? Ethan? It's continuous. Hopefully you can work that out, alright? So what I've got is a piece of lead, okay? Now lead is not made up of a whole lot of particles, okay, like this. It's continuous. Obviously it's extruded into that shape, alright, but the point I'm trying to make is that metals are one of those criteria where the structure is not just one little piece, but it's lots and lots of pieces joined together. So we define that as being a continuous structure. Yes, and we talked about ionic compounds, we talked about continuous covalent compounds on Friday. The only one that wasn't continuous was, what do we call these? Covalent. Thanks, Jaden. So covalent, we said, is not continuous. They're separate, okay, whereas metals are continuous. Some terminology, okay, that we need to understand, all right, for metals and metallic bonding. I've used the word delocalised. That's what the textbook uses. Delocalised means basically it doesn't really hang around in the local area, all right? If you were delocalised from this classroom, for example, you would be out there, someone would be over there, someone would be in the next room, but you'd all be sort of more or less, all right, linked to this classroom, but you wouldn't all be in the same room at the same time. No different to how electrons work in a metal. Okay, so electrons in a metal are not actually attached to every single atom. So I'll say that again. So none of these electrons actually say, oh, I actually actually came from that copper, or I actually came from this copper. Maybe I did, maybe I didn't, all right? But the whole point I'm trying to actually make is that the electrons that form a metal, we call them actually delocalised. They don't really belong to any copper metal, but they did come initially from a copper metal, or a copper ion in this instance, okay? When we draw a metallic structure, we draw it like this. Mohammed asked, what does that mean? Well, if I were to look at this under an electron microscope, okay, that's really what a metallic structure looks like. A whole lot of little balls, okay, copper ions all these are, okay. I'll just make it more later, okay. So these are all copper ions, okay. If you can imagine a structure, all right, like that, not too hard to conceptualise, I hope, with this stuff here. And in between that, all right, there is the electrons that flow between those holding them together. A bit like the glue, okay? All right, that's a concept of what a metal looks like. This happens to be copper, and in a minute we're going to draw things like, we're going to draw iron, we're going to draw aluminium, we can do some lead as well. What we want to look at are the properties of some, look, that's just showing, look, that metal is actually ductile, alright? What does ductile mean? Ductile? Zach? It can be made into long bits of wire, another piece of wire, okay? And so I can easily tear off, okay, and this will be done with a machine, but I can easily actually rearrange the shape of metals. It's unique to metals, by the way, alright? Metals have got that property that because the way the atoms are bonded, they're actually not locked into a structure, okay, as you can see, alright, but there is a force of attraction. So I can actually pull apart or make this into wire. This is really how it looks, okay, in real time. This is what we're doing. Of course, I don't think you'd ever get a piece of wire that was one atom thick, alright, or one cation thick. That would be fairly unique, alright, but this is the simple way of looking at it. This is what we're doing when we actually form a piece of copper wire under really high strength, alright. So that means that we can actually take, alright, a piece of metal, and under the right conditions we can put it into a piece of wire, okay? So these are not locked in, it's just a shape, alright, that I can modify over and over again. Not all metals, by the way, but most metals have got that property. Malleable. What does malleable mean? Ethan?
To be like bent in shape.
To be bent, okay. So here I've got stainless steel, this is not aluminium, this is a stainless steel drink bottle, okay? And of course it would have started off with a lump of stainless steel, and it would have been moulded into that shape, or probably pressed into that shape, alright, using some fairly high tensile, fairly large dies, which is how they stamp out, you know, sheets of metal for cars, for example. So that is a property of metal. It's really important, okay, and we use it all the time, believe it or not. So if something's malleable, it means we can reshape it, and I'm just playing with that in my hands, so I can actually shape that metal really into any shape that I want, okay? And if I'm not happy with that shape, then I can reshape the metal, alright? If anyone has ever done an apprenticeship for panel beating, alright, they actually show the panel beaters how to actually modify the shape of a metal using certain tools, alright? And so that's the whole thing with steel. You can actually reshape the steel. Same with copper, alright, you don't use copper in a car for obvious reasons, why not? Number one would be the strength. Number two would be the cost, okay, it would be exorbitant, alright? So you're not likely to use copper in a car, alright, for the panels of the car. It's going to be not strong enough for the first instance. It's going to be good for corrosion, mind you, and not good for a conductor though, or very good for a conductor, which is probably what you don't want. So each of the metals have got slightly different properties, but they're all, apart from one of them, are going to be malleable and ductile. High melting point. Why do you think metals have got a high melting point? Ethan?
Because they have a low amount of energy, like they're solid.
High melting point. What does that mean? If something's going to melt, if I'm going to melt this, I've got to do this. I've got to take that out there. I've got to take this one off, put it there. Not very easy to do, okay? And so if I'm going to melt a metal, alright, I've got to actually break all of these little bonds, okay, in my lattice. They're not actually bonds, just forces of attraction holding the metal ions together, okay? So we've got to break those bonds in order to melt it. Tells you something about metallic bonds. They're fairly strong. Make sense? Okay, so I'll put that back again, alright? Turn it back into a solid. Why are they conductors of electricity? Because, so how do we explain that? You're going to do that in a minute in a table, but how do we explain that a metal is a conductor of electricity? What is electricity? I'll go back one step, and if I ask you, what is current electricity?
Flow of electrons.
Flow of electrons in a conductor, or normally in a wire, okay? So if I were to actually put into this a power source, okay, and if this is the positive side, negative side of my battery, what's actually flowing in a current? In a piece of wire, it's electrons. So the electrons have to be mobile. So what in the metal then makes it a conductor? The ions are what makes it a conductor. Wait a minute. These are the ions, these are the cations. Do the cations move? No, they don't. So what's moving in the metal when I put it into a circuit? The electrons. Okay? So the structure of a metal, okay, remember, is positive ions. The positive ions are locked into a lattice. There it is. Okay? Some sort of an ordered structure. But between the lattice, there's a mobile sea. I use that terminology up here. Mobile sea of electrons. So those electrons can be forced to move with a battery, or they can be forced to move with heat. What are we doing when we heat a metallic object? What are we doing? So if I had a Bunsen burner, and if I started heating this at this end, if it was a copper wire, let's assume this is lead, but let's assume it's a copper wire, okay, and I was standing here with my piece of copper, and I was heating it in a Bunsen burner, eventually what's going to happen, Lewis? The electrons
Are going to move faster?
Good, faster is what I'm after. Okay, so what will happen is this. As we heat the metal, the electrons here and here are going to move faster, which means if they're moving faster, what are they doing with the energy? They're absorbing energy. They're undergoing like an endothermic process. So the electrons are absorbing energy. If they're absorbing energy, they're moving faster. Okay, they collide with the next set of electrons, which moves to the next ones, the next ones, the next ones, and so on. And depending on the sort of metal we're talking about, depending on how many free electrons they have, it's either going to be a good conductor of heat or a poor conductor of heat. Most metals are good conductors of heat, as my son found out. Okay, so when my number 2 son Tyson was only about 7 or 8, obviously he hadn't learnt much about heat and conductivity. My other son, we were at a campfire. He had a beautiful piece of steel rheostat, you know, stuff they put in foundations. So of course, being boys, they're sticking this in the fire. So he left it in the fire. We went off somewhere, and we came back, and my son picked this thing up, and he said, "Oh," but he actually yelled it out quite loud. Okay, and when he took it off, he had the pattern, the beautiful pattern, the coil even, okay, of blisters in the middle of his hand. Okay, had to rush him off to hospital and all sorts of stuff. So he learnt the hard way about metals' ability to conduct heat. Well, we're on that in terms of other properties and other metals. This is the exception. I can't give this to you. It's in a double insulated container now. I've got to fill out a massive risk assessment for this in a minute anyway. So this is mercury, okay, and as we know, mercury is the only exception to the idea of hardness, malleable, ductile, melting point, etc. It does tick the conductivity of electricity, and it does tick the conductor of heat, because we use mercury in what? Thermometers, mercury thermometers, okay? So obviously it's a good conductor of heat, and everything, or most metals, will expand when they're heated. So we use that property there. So mercury is the only exception to this one. It's obviously melted at room temperature. It's got a very low melting point. Some other properties of metals that you may or may not be aware of. We've got a bit of lead here. Okay, so as we know, lead is extremely, malleable. You can melt lead, pretty low melting point actually. When I say low, low compared to metals, but greater than 200. So if I had a hammer, and if I had a die, I can take this piece of lead, all I've got to do is slam it a few times, and it'll end up looking like one piece of lead, all right, if I wanted to, or I could melt it, all right, in a Bunsen burner flame, and remould it, all right, into a lead zinc or something like that. Lynn?
Doesn't lead have a high density, it's not as heavy? But really, why do we have a low density?
It's got a high density, yeah. High density is the atoms per square, or per cubic centimetre, okay? But it's nothing to do with the hardness. We don't equate that with the hardness of the metal. You would think you would, but it doesn't work. Piece of aluminium. Now, think I spoke about this last week, but aluminium has not got a very good tensile strength. What does that mean? It's still malleable, okay. Oops, what happened?
Snapped it?
Snapped it. So what does that tell you about aluminium in terms of the way that the aluminium atoms are bonded together? Probably not, no. So aluminium has got slightly different properties. It's still malleable, mind you, but aluminium is a sort of metal that you can only actually flex it, you can only actually put it under stress so many times, and you keep on going, and you keep on going, and eventually it will reach a point, all right, where you've exceeded the tensile strength, and it breaks very easily. Whereas lead, doesn't matter how many times that with lead, okay, these ions are bonded slightly differently, same structure in the background, but we can do that sort of continuously. So basically what you need to get in relation to what a metal is, all right, oh, it's metal, get off, all right, is we need to be able to draw the structure for a metal. We have to understand what we mean by delocalized or mobile electrons, straightforward. And Michael, we need to know all these properties, and these properties, by the way, once you understand the structure, all of these properties, okay, we relate back to the original structure. Once you understand that, you've got the concept of metals nailed, okay? And this is, I think, the best way I've found to try and demonstrate how metals actually look and how they work, okay? If you've got these things, bring them along. You can play with those as well.